Hello Science Alliance, and thus begins our lesson on specific heat capacity. Why is it the filling? In the 90s, when I was growing up, we used to have Pop-Tarts. Like, they've still got them, but we used to just have them routinely as if they were okay. It was pastry as a rectangle with jam inside, and they had to release all these warnings because there were terrible stories in the newspaper about children who'd been given a Pop-Tart, like, oh, this pastry is just the right temperature, thanks, and then burns their mouths because the jam was really hot. Why can you put something in a microwave for and all of it be cooked for the same amount of time, but you bring it out and some bits are really hot, some bits are not really hot? In an attempt to make specific heat capacity interesting, I asked you to bring a metal spoon and some water. It would be better if the spoon and the water had the same mass, but it doesn't really matter. There's new people joining live. If you've just joined, you've not missed anything. No offense to the people who've been here since the beginning. What I'd like you to do, please, is just hold the spoon in your hand. Maybe hold the spoony bit so that you've got a lot of metal in your hand. Hold the spoony bit of the spoon. And also, can you, if you don't find the feeling too unpleasant, can you put your hand into the glass of water? So you've got your hand in a glass of water like this, and you've got your hand on a metal spoon. I want you to imagine, right, that you're a detective. You burst into a room. The criminal has just left. Your colleague chases after the criminal. It's your job to inspect the scene and find out as much information as you can about what's been happening in the room, but you've only got thermometers. Last lesson on Facebook when I did this yesterday, everyone just now started talking about what kind of terrible crime could have been committed that involved someone holding a spoon and putting their hand in a glass of water. It doesn't matter, okay? It doesn't matter. Just, how could you tell if you now let go of the spoon and you take your hand out of the water, you've got thermometers, how can you tell that someone has been holding the spoon and someone has had their hand in the water? Can you tell? Just using your thermometers. Is it possible for you to get that information? Drying my hands. You can't get the information about the water, can you? Not using a thermometer. I can hold my spoon now, and it's still really obvious that someone has been recently holding the spoon because the spoon is warm. But the water, I mean, I haven't got a thermometer, but we would not see any temperature change, would we? It hasn't made any difference. If you put your hand into the water now, you'll find probably, if it's like mine, it's still quite chilly. It's certainly colder than my body temperature. Why? Why that difference? Well, it's because of something called specific heat capacity. Specific heat capacity, are you ready? Is the specific heat capacity of a material is the amount of energy required to raise the temperature of 1 kilogram of the material by 1 degree C. The specific heat capacity of a material is the amount of energy required to raise the temperature of 1 kilogram of the material by 1 degree C, right? It's how much something can kind of store energy, if you like. It's the amount of energy you've got to put into something to raise its temperature, to make it hotter. So if you came to my all ages lessons about weather and climate fairly recently, we were talking, I think it's fairly a well-known fact, that in the summer, sun shines on the planet, the land heats up like almost straight away and gets very hot and sweaty. But if you go to the seaside, it's a bit cooler because the sea is cooler. But in the winter, the sea is actually warmer and the land is cooler. It's because the sea and the land have different specific heat capacities. So the sun shines on Earth, it just gets hot straight away. You don't have to put much energy into the Earth, the land, to raise its temperature. Whereas the sea, you got to put absolutely loads of energy in to raise its temperature. It takes pretty much the whole summer for the sea to get warm. And then again, because it has a high specific heat capacity, it takes a long time to cool down. So the land cools down straight away, but that's why being near the coast is actually supposed to be a little bit warmer in the winter. So water, well, yeah, kind of sort of told you. I was going to say, which one of these, the metal or the water, do you think has the highest specific heat capacity? Specific heat capacity, the amount of energy you have to transfer to something to raise its temperature. Which one has the highest specific heat capacity, the metal or the water? Loads of people on Facebook were saying the metal, and I can completely understand why, because you think like you've got to put a lot of energy into metal to melt it, right? This metal is a solid, you'd have to heat it up a lot to get it to turn into a liquid. This water is already a liquid. Even at room temperature, it's warm enough that the bonds are broken and it's become a liquid. But actually water has a really high specific heat capacity. I don't know whether it's, I don't actually know if it's because like the particles in the metal are closer together, so like obviously it's a good conductor. Anyway, water has an incredibly high specific heat capacity, one of the highest of all the kind of objects that you will find around the place. What, I can hear you crying, is the equation for specific heat capacity. Just a few deep breaths here, a few deep breaths. You ready? Here it is. It's energy, like the amount of energy that you put in, equals mass times the specific heat capacity of the thing times the temperature change. And if we were going to write that as symbols, keeping my voice very quiet now, it would be change in E, like the change in temperature. This little triangle is the Greek symbol delta, that means change in. Change in energy equals M, which is mass, times C, which is the symbol for specific heat capacity, times change in again, delta, change in the Greek symbol theta, which means temperature. That's all right, isn't it? And in case you were loving that too much, then we don't usually put the times symbols in equations, so it just looks like this. Isn't that brilliant? Change in E, the sort of change in energy, the amount of energy that you have to shift to the thing, equals the thing's mass times its specific heat capacity times the change in temperature. I know, don't worry, it's going to be fine. Just bear with me. Okay. I don't like teaching you maths. I haven't ever really done it because in the classroom people just sort of come in knowing maths because some other poor souls had to teach them maths. But I have got brand new pens. I think very quickly we'll do a really awful lazy shortcut in how to arrange equations, okay? So let's imagine that we've got just, oh wait, I can write forwards because I'm on YouTube. Let's say we've got 6 equals 3 times 2. Are you okay with the equal sign means that they are both exactly the same? It's the same. A 6 is exactly the same as saying 3 times 2. So if you want to mess around with this equation, I'm just going to show you the quick lazy way. If you want to rearrange this equation, whatever you're doing on one side, you have to do the opposite on the other side. So if for some reason you want to get 3 on its own, like 3 equals something, you've times by 2 on this side. So if you're going to move the 2 over, you have to divide by 2 on the other side. I don't think that a maths teacher would like this, but we're working fast here, people. You can go away and work out how to rearrange equations on your own properly if you want to. But now I would end up with this equation here, wouldn't I? I think these new pens could be thicker. So now if we've done that rearranging, we've got 6 divided by 2 equals 3. Is that right? Yeah, it is. So we have rearranged correctly. And it's just the same. You'll have noticed that this specific heat capacity equation has 4 things. We've never worked with an equation with 4 things before. Let's say that 2 times 2 times 3 equals 12, right? 2 times 2 is 4. Times that by 3, you get 12. So now we've got 4 things. What do? Well, let's say you want 3 on its own. It's just exactly the same, but you can just lump things together in brackets. So if I want to get 3 on its own, like 3 equals whatever, I can just put that in brackets and then move it down here. So I've timesed by 2 times 2 on this side. So I've got to divide by 2 times 2 on this side. So this, if I work all that out, would end up with 3 equals 12 divided by 2 times 2. Is that right? 2 times 2 is 4. 12 divided by 4 does equal 3. So that's how I rearrange equations in my head. I'm gonna give you some questions, but I'm not gonna make you rearrange the equations to get the answer to the question. But it wouldn't be a very good lesson on specific heat capacity if I didn't ask you to rearrange a little bit. So I'm just gonna give you like 20 seconds. See if you can rearrange the specific heat capacity equation to make M and C and change in theta, like change in temperature, the subjects. If you absolutely can't do this and you are finding this terribly unpleasant because you're out of your comfort zone, don't worry about it. I mean, you don't even have to do it. Like, just have a drink of water. We're finished with it now. And then you can go away and work out how to rearrange equations in your own time. I'm one of these people who needs quite a long time to think things through before I get it. But anyway, I will be silent for 30 seconds and let you do this. I'm just tutting at my whiteboard pens in the background. Oh, they were expensive as well. They're refillable. They're just a bit thin. Anyway. How have you got on? So the first one, you can sort of put the C and the change in temperature in brackets and move them both over to be underneath the E, okay? So you should have M equals change in energy divided by C times change in temperature. And the C, I mean, they're all pretty similar actually. You're all just sticking things underneath the change in E. So C, specific heat capacity, equals change in E divided by M times change in temperature. And giving you like a fraction more thinking time. Change in temperature, again, you just take those two, they're times on that side, so you've got to divide on that side. So it's change in E equals, change in E divided by M times C equals change in temperature. Right. I better give you some questions then, haven't I? You don't, like I say, you don't actually need to know that, you don't need to remember that for this lesson. Here's some questions. I've given you some information at the top. The specific heat capacity of water is 4,200 joules per kilogram degrees C. Okay. The specific heat capacity of aluminium is 880 joules per kilogram degree C. So I've asked you, please, can you tell me how much energy do you need to raise the temperature of 2 kilograms of water by 1 degree, 5 kilograms of water by 0.8 degrees, and 300 grams of water by 4 degrees. And you've got the equations here, right? This means the change in energy, like sort of the amount of energy, equals mass times specific heat capacity times change in temperature. And I've given you the mass, it's 2 kilograms, and you've got the specific heat capacity of water up here. And you've got the change in temperature, because the change in temperature is just 1 degree, right? That's how much the temperature has changed by. So for the first ones, you can just plug the numbers in, actually. Question number 4 is, how much energy does a 3 kilogram block of aluminium lose when it cools from 200 degrees C to 50 degrees C? Oh, specific heat capacity. Oh, I mean, I'm a physics teacher. I'm supposed to love you all equally, but my goodness me, it's not one of the most dramatic revelations of a lesson, is it? And question number 5. A pan contains 0.5 kilograms of water, which is at 6 degrees C. Whoa! If you shift 3,150 joules of thermal energy to the water, what is the water's temperature afterwards? If you're watching this on catch-up, you can't see, as I can see, people just dropping off. It's like busking this, honestly. In a classroom, teaching specific heat capacity wasn't sort of the most fun I'd ever had in my life, but at least people couldn't just leave. They weren't allowed to literally just get up and leave. So if you're watching this on catch-up, thank you. I appreciate your presence. I'll give you a few more seconds and then I'll go through the answers. I'm going to leave the last 2 questions on the board while I go through the first ones, so if you're not quite finished, you've got a chance to catch up. be really careful on the last one. Okay, should we have a go? So like I say, I'll leave the questions 4 and 5 on the board just in case you want a little bit more time. How much energy do you need to raise the temperature of 2 kilograms of water by 1 degree C? Well, like I say, you want to know how much energy you need to put in. So it's this top one, change in E, that you need. You've got M, the mass, you've got C, the specific heat capacity of water, and you've got change in temperature. So you just plug it in. And the answer is change in temperature equals 2 kilograms times 4,200 times 1 degree. So you should have got the change in E equals 8,400 joules. Can you spot the deliberate mistake that I made in that answer? There is a mistake there. I'm not proud of myself. Did I forget to change it before this YouTube version of the lesson? Yes, I did. But you might as well learn something from me if I'm going to leave this mistake on the board. You see the mistake? It's a units mistake. The mistake that I have made is, well, should we do it? Let's do it. Didn't do this yesterday. Some new pens. You just can't really see it, can you? Right, we've got change in E. That's rubbish. These were very expensive. Change in E equals Cm change in temperature. If we rearrange that to get specific heat capacity, I want C on its own. I brought all the refills as well. I spent a fortune on the refills. I'm furious. If we rearrange it to make C the subject, how are we going to do that? So change in E is still going to be on the top, but we're going to put M down there, and we're going to put change in temperature down there as well. So what are the units of specific heat capacity? Well, it shows you, doesn't it? Energy, you don't worry about the change in. The unit of energy is the joule. So it's a joule divided by the unit for mass, which is a kilogram, and the unit for change in temperature, which is degrees C. It's not mass divided by temperature, it's just mass temperature. So you just write the units next to each other. So it should be that, but I've done that, slash, which is wrong. There we go. 2 packets of these pens I bought in order to get free postage. How much energy do you need to raise the temperature of 5 kilograms of water by 0.8 degrees C? Again, it's just the same thing, right? You just plug the numbers in. So it's 5 kilograms times 4,200, blah, blah, wrong units, times 0.8, which is 16,800 joules. Well done if you got that. 16,800 joules. And for the third one, did you notice that it was in grams and you had to change it into kilograms, yeah? If you're going to change 300, you've got to change it. If you just put 300 into this equation, the equation will think that you mean 300 kilograms. So first of all, you had to know that 300 kilograms is the same as 0.3 kilograms and convert it. And then, again, just plug the numbers in, and you should have got the answer 5,040 joules. 5,040 joules. And question 4, what was... well, that's not really anything too sneaky there. Some people were getting confused on Facebook about the fact that it was losing energy instead of having energy put in. But it's change in energy, so that's absolutely fine. So the answer to that one, well, first of all, you needed the change in temperature. And it started at 200 degrees C and it finished at 50 degrees C. So the change in temperature was 150 degrees C. And you just plug that into the equation again. And that tells you the change in temperature, like how much energy it's lost. So it's 3 kilograms times 880, because you're talking about aluminium. Be careful, you're not talking about water, so it's a different specific heat capacity, times 150, which gives you the answer 396,000 joules. 396,000 joules. And it was this final question that was causing people a lot of problems on Facebook yesterday. You got that? 396,000 joules. A pan contains 0.5 kilograms of water at 6 degrees C. You put 3,150 joules of thermal energy in. What is its temperature afterwards? So you're looking for the change in temperature, right? You've got to use this equation here, the second one. Change in temperature equals change in energy divided by mass times specific heat capacity. So it's the change in energy, which they've given you, the amount of joules that got shifted, 3,150 joules divided by the mass times the specific heat capacity of water, because you're thinking about water. So the answer is 1.5 degrees C. And then on Facebook, everyone got really upset. and started saying, wait, this is water that's been heated up. Why has it got colder? Right? It starts at 6 degrees C. It gets heated up. And now you're telling me that the answer is that the temperature is 1.5 degrees. They were saying in the Facebook comments yesterday. Why has the water cooled down? So I said, oh, you tell me, why has the water cooled down? Even though it was on the hob. And they all started saying, oh, because you're stirring it. So as you're stirring it, it's increasing the amount of evaporation. And I was like, oh, so glad we did this. No, just no. I mean, in practical, real life, stirring something when it's on a hob does not make it cool down, does it? You don't put soup on a hob, start stirring it with a wooden spoon and then find that, oh no, the soup has got colder. No, it's what I didn't say on Facebook. I was ever so polite. I said, the answer is, this is the change in temperature. You haven't actually answered the question yet. It's what is its temperature afterwards. So if it started at 6 degrees C and it changes its temperature by 1.5 degrees C, the temperature afterwards is the original temperature plus this change in temperature, which is 7.5 degrees C. Whew, God, YouTube, I feel better for getting that out of my system. So the actual answer, right, the final temperature, 7.5 degrees C. Okay. For your IGCSE, if you're going to do it, and you know, just out of interest, because obviously this whole thing is fascinating, you need to know about an experiment to find the specific heat capacity of a substance. Usually with the experiments, I just point you to usually Lewis, who I know and really like. He's great doing, he's got all the kit and he just does the experiment on YouTube. So you can watch him, and he even leaves so that you can just make the notes yourself and do the graphs. It's very good. And BBC Bitesize have got something about it, but I felt like there were just a few details missing that might be confusing. So I'm going to run you through briefly the experiment to find the specific heat capacity of a thing. Ask a few questions that came up that I think you might also have, and then you can watch Lewis do the video and hopefully it'll make more sense. So, experiment to find the specific heat capacity of aluminium. What you do is, you get a 1 kilogram block of aluminium and you take the mass of it using a balance. I know everyone in the entire world says scales, but when you're a physicist, you need to talk about a balance. It's a set of scales, but it's called a balance because it's finding the mass of something, right? Not the weight, not how much the force is pushing down, but the weight in kilograms. The mass in kilograms. So this is a balance. You put the 1 kilogram block of aluminium on the balance to find its mass, right? That's the first step. And then you put an immersion heater in the block. Here's what an immersion heater is. It's a little heater, like on a stick, that you can immerse into things, okay? So you put the immersion heater into this big hole, which is in the block of aluminium, and you put a thermometer into the other hole, and then you record the temperature, right? And then you wrap the whole block in insulating material, and you connect an ammeter, which measures current, and a voltmeter, which measures voltage, to the immersion heater, connect the whole thing to a power supply, and you turn it on, right? And then you just leave it for 10 minutes and allow the aluminium block to heat up, and you record the ammeter and the voltmeter readings. When you switch the heater off, the block gets slightly hotter for a few seconds, maybe because conduction. So you record the hottest temperature that it gets to. Okay, that was very fast, but basically at the end, because we won't go into it because we did this in our electricity lessons, but because you've measured the current and the voltage and the amount of time the heater was on for, you can work out the energy from that, right? Using the power equation. Doesn't matter if you haven't done that yet. So you've got how much energy went into the block. You've got the temperature change because you measured the temperature at the beginning and the hottest temperature it got to the end. And you've got the mass of the block. So you can work out the specific heat capacity of the aluminium. Hooray! So I read that and I had some questions initially, and I thought you might as well. Take the mass of the 1 kilogram aluminium block. Why would you do that? It's written right there. It says it's a 1 kilogram aluminium block. Why would you then take the mass of it? Put the immersion heater into the block. Put the thermometer in the other hole and record the temperature. I've said, can you spot any problem with this? Can you think of a solution? What's the problem? Put a thermometer into a hole, measure the temperature of the metal. Any problems there? Have you got a solution? And why do you wrap the block in insulating material before you turn the heater on? I'll let you, I don't know, think or scribble for 10 seconds. I'll give you the answer. Have you written something down? Have you scribbled? Okay, so to take the mass of the 1 kilogram aluminium block, this wasn't really causing any problems on Facebook. It's just to check, innit? Just to check the manufacturer's label is correct. When Lewis does it on YouTube, he finds that his is ever so slightly heavier, which might affect his results. So he writes down the proper mass, not the mass that's on the label. Any problem with putting the thermometer in the hole? Well, it's just not. It might not be a very good connection, mightn't it? Like, is the thermometer actually completely touching the metal, or are you going to end up measuring the temperature of the air in the hole? So I've put might be measuring the temperature of the air, so add some oil to the hole. Lewis actually adds water, but most of the write-ups for this say you should add oil just so you've got a good connection between the metal and the thermometer. And you wrap it in insulating material so that the heat doesn't escape, or so that all the heat that you're shifting into the block is transferred to the block, not the surroundings. Because obviously if loads of the heat is escaping, then you would end up thinking you needed to put more energy in than you actually would, if that makes sense. Okay, so I think you've got enough there to be able to like watch Lewis's video and get all that. Finally, I've just got one tricksy little question that I was really proud of. They all just got it right straight away on Facebook, which disappointed me, but I thought this might not be totally obvious. The equation again for specific heat capacity, energy equals mass times specific heat capacity times temperature. Or if you like, specific heat capacity equals change in energy divided by mass times temperature change. Does the specific heat capacity, please, just before we go, this is your final question, does the specific heat capacity of a substance depend on its mass? Does the specific heat capacity of a substance depend on its mass? Yeah, they all just got it straight away. I didn't think it was that obvious. No, it doesn't. I was thinking you might think that because it's in the equation, that if you change any one of those things, then you change the other thing, right? Like in a sum, 3 times 2 equals 6. If you change the 2, you also change the 6. But that is not what happens. Specific heat capacity, obviously heat capacity means like its capacity to store heat. But the word specific actually means that it doesn't depend on the sort of shape or the size of the material. Sorry, my husband is blowing his nose so loudly, it's very distracting. It's a bit like, imagine that you were calculating the speed that someone would run a 100-metre race. The equation you'd use would be speed equals distance divided by time. So speed equals, say, 100 divided by 12 seconds. If you're trying to find the person's speed, you can't just be like, oh, well, I'll change the distance and then that'll change the speed. Like that wouldn't be how it worked, would it, in real life? So yeah, in real life, the specific heat capacity of the object stays the same. So, have BBC Bite Size made a mistake here, please? This is the last question, honestly. Here we go, BBC Bite Size. I'm actually going to ask you to read this in the homework PDF that I post up in my Facebook group every week. It's there already. That never happens, but it is already there. They say specific heat capacity, heating materials, blah, 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 blah. Different materials require different amounts of energy to change temperature. Fine. The amount of energy needed depends on the mass of the material, the substance of the material, so the specific heat capacity, and the desired temperature change. Have they got that right? The amount of energy needed depends on the mass of the material. Have they made a mistake or have they got it right? The amount of energy needed depends on the mass of the material. They haven't made a mistake, have they? It's totally fine. The amount of energy needed does depend on the mass of the material. If you think of that equation again, the amount of energy needed definitely depends on the mass. If mass is really big, then you need to put a lot of energy in. But also, if mass is really big, you put a lot of energy in. But if mass is really big, then the temperature change would be really small. So it all works out. What is the case is that the amount of energy needed definitely depends on the mass of the material. If it's really big, a lot of mass, you need more energy. But specific heat capacity doesn't depend on the mass of the material. All the desired, it doesn't depend on anything, it just is what it is. Does that make sense? Phew. Right. And thus ends our lesson, she says, trying to conceal the relief on her face. This ends our lesson on specific heat capacity. Next week, I think it's the last lesson in this module next week, and we're going to be doing the Kelvin scale, which is something that I do genuinely find very interesting. We're going to look at sort of how you measure temperature and how there's a Celsius kind of doesn't really make any sense, and the Kelvin scale is very cool. Right, if you are enjoying these videos, if you're enjoying, I sort of think of them as lessons more than videos, but anyway, if you want to support me, you totally can. You can go to my about section on YouTube, or if you're on my website, then there's a link that says sign up where you can support me on Coffee. So how it works is everything that I do is free, and yeah, like I say, I do free printouts of these lessons, which are on my website. The lessons are obviously free, and just for you IGCSEers, I've got a PDF in my Facebook group of like past paper questions that I found that I think you should be able to answer once we've done the lesson, and also, like I say, sort of videos that I think might help your understanding so that you can take it a little bit further. Hey! Tiger and Bird are still here. Oh, fabulous, brilliant, hello. And Ollie and Evie are here as well. Ah, great, oh, that's amazing. You've like doubled my audience, you guys, already, straight away. Brilliant, thank you. Because I thought there was one, and there's actually two for every one of my numbers. Thanks you lot, that's nice of you to say hello, just on my Facebook page. So yeah, if you want to support me, if you haven't already, then you can click my about section, follow the link to Coffee. I send you nice things. I send you Theatre of Science magazine, which is very good actually. I'm very proud of it. And yes, and you get a nice feeling that you are helping me, not like helping, like you're actually the reason why I can do this job. So thank you so much. Right, yep, I'll see you next week. In fact, I might advertise that lesson right now. I'll be so organised. Yeah, I'll see you next week for another IGCSE lesson, or I'll see you tomorrow if you like my YouTube things at 9 AM for the all ages polar regions lesson, or 10:30 AM for the Lego Story Show, which is on Titanic at the moment. Okay, I'll see you soon.